Let me check. I want to say that this is a one chapter test.
Oh, since that's right. No. But if it wasn't, what would it
Let me just. Not sure. Yeah, this is a one chapter test, so we have 2 more lessons today and tomorrow. So,
That would what make test?
Monday. Darn, Monday tests. We could do a Sunday night study session after Sunday church if you want. Okay, we'll talk about that later. But okay. All right. Mr. Le Chatelier. This name should at least look familiar, hopefully. We talked about it in the dreaded equilibrium chapter last year. I know some of you didn't think it was super dreaded, but yeah. Anyways, open your books. I'm just going to read like 3 paragraphs or 2 paragraphs, and then we'll talk about the effect of changing concentration. We'll be done. 620. Of all the things in chemistry, I mean, a lot of it is applicable to a lot of things, but I will say equilibrium and the idea of Le Chatelier's principle is probably the most used or most useful idea or concept that is being used today. What I mean by that is from a production standpoint, everybody wants to produce more product, correct? It just makes sense. You can produce more product, you can get more money, okay? And so from an equilibrium standpoint, there's one equilibrium at a given temperature. However, there are a few things that you can do to make the equilibrium shift one direction or the other. And you can imagine if you want to produce product, you'd want to shift it so you produce more products. Okay? So this idea, along with the equilibrium concept, is probably the most used today. In fact, when chemists get hired at production plants, that's what they do. Try to optimize or make the reaction produce more product. Okay? So I'm just going to read beginning at 13.7, just a couple paragraphs, and then we'll get into it. It is important to understand the factors that control the position of the equilibrium, or of a chemical equilibrium. For example, when a chemical is manufactured, the chemists and the chemical engineers in charge of production want to choose conditions that favor the desired product as much as possible. That makes sense. That is, they want the equilibrium to lie far to the right. When Mr. Haber was developing the process for the synthesis of ammonia, he did extensive studies on how temperature and pressure affected the equilibrium concentrations of ammonia. Some of his results are given in the table below. Note that the equilibrium amounts of NH3 increases with an increase in pressure, but decreases as the temperature increases. You can look at the little table there at the bottom and see that. Okay? Then, continue on here. Thus, the amount of NH3 present at equilibrium is favored by conditions of low temperature and high pressure. However, this is not the whole story. Carrying out the process at low temperatures is not feasible because the reaction is too slow. So not only does a chemist have to understand the equilibrium side of things, but they also have to understand what side of things as well. What is the other thing that's super important? Based on that last statement. I'm not answering this, I'm waiting for you. It's not a hard one. You can sit there and wait for me to give you an answer, and it's not happening.
Which statement?
However, this is not the whole story. The Equilibrium's not the whole story. Carrying out a process at low temperature is not feasible because the reaction is,
I mean, there's a lot of other variables.
okay, well, what is the main idea that deals with how fast or how slow?
Catalyst.
What's the vocabulary? Big word. Last chapter, we talked about it. I mean, that's part of it. I'm not saying it. Look at the heading in chapter 12. Do it. Just turn to chapter 12, beginning of chapter 12. Kinetics. Kinetic studies rates, how fast. Great. We can have a chemical equilibrium lie as far to the right as possible. But if it's slow as molasses, are we going to do much? Or do much of anything? No. Okay, so yes, it does depend on a lot of factors. Now, does activation energy play a part in kinetics? Absolutely. Does concentrations and things like that play a part on the kinetic side? Absolutely. Okay. Continuing on here. Even though the equilibrium tends to shift to the right as the temperature is lowered, the attainment of equilibrium would be much too slow at low temperatures to be practical. So great, you can get to the far right, but it takes forever, so not real practical. This emphasizes once again that we must study both the thermodynamics and the kinetics of a reaction before we really understand all the factors that control it. We can quantitatively predict the effects of changes in concentration, pressure, and temperature on a system at equilibrium by using Le Chatelier's principle, and here's what it is. If a change is imposed on a system at equilibrium, the position of equilibrium will shift in the direction that tends to reduce the stress or the change. Okay? So, when you're stressed, right? When you guys are super stressed, you guys just love to wallow in that stress and just maintain that stress, right? No. What do? Yeah, you try to do whatever you need to do to reduce or to eliminate your stress. Same thing for a chemical reaction. If I put a stress on a chemical reaction at equilibrium, it is going to proceed in a way that can undo that stress. Okay? And that's really what Le Chatelier's principle is. If I add reactants, if I add products, if I remove, it will shift in a direction that will reduce the strain that's being added on that particular chemical reaction. And we're just going to talk about the concentration effects today. And maybe I probably could take about 5 minutes and just say, here is what happens when you add the concentration, or here is what happens when you add or remove concentration. And you guys would probably be fine, but I'm going to try to at least give you kind of how it relates to everything here. So, nice little blank spot here. Which one's good? Okay. Change in, nope, I don't want to write that. Can I just use brackets to represent concentration? Is that all right? Give you an example here. Okay. Let's consider an equilibrium position here. Where you've got the equilibrium concentration of N2 have the equilibrium concentration is the Haber process that we've kind of talked about quite a bit. We have this. The question we want to ask is, what will happen I'm going to write the K value for this particular situation. All right, so we want to figure out how changing a concentration of something, how it will affect the state of equilibrium. Okay, so I gave you up there 3 concentrations at equilibrium. So I know that my rate of my forward reaction and my rate of my reverse reaction are going to be the same. And then I induce a change or a stress. What is the stress in this context? I'm adding a reactant. You guys want me to write the equation, or are you guys pretty familiar with the ammonia? Oops, that's not it. Okay. Is there any way that we could, based on what we have done last couple days, figured out if this is going to affect equilibrium or not? Is there any way we could figure out if this is going to shift one way or the other, or if it's not going to shift at all?
Or the Q.
Yeah, find the Q and compare it to, yeah, so let's do that. If I add 1 molar N2 to this situation, once you figure out what our Q is, we got it? Try it out when you get it out.
0.02. Oh wait, no. Q film.
Times.
That's 10 to the negative 2.
Really?
You didn't cube it?
Did you double parentheses everything? Otherwise it might have multiplied by it.
I usually do it 1 step at a time.
Oh.
I got 1.
You did? Okay. All right. So, with this information, can we figure out if we stayed at equilibrium, if it's going to have to shift one way or the other to get back to equilibrium? How do we figure that out? Alright, so shift right, anybody have any seconds on that, or? Okay.
Doesn't it shift what? Q is bigger?
Q plus.
Q is actually less than.
Oh.
It's kind of, those negative exponents are tough sometimes to figure out. Q is less than Okay, so we'll shift right. Okay, well, based on that, the result should be an increase in what? What will increase if I shift right? And a decrease in reactance. Why? Well, I mean, Q is just a variable. I mean, where's the Y in just saying, oh, we know Q and how it relates to K, but what's the real reason behind this? Why did all of a sudden we produce more products when originally our rates were equal?
Because we added more again.
Okay, what is adding a reactant going to do? Think about, we're kind of going back to last chapter. I know we struggled going back a chapter or two. We just saw that today. But if we go back a chapter, we talked about rates. It speeds up what? Like speeds up the forward, speeds up the reverse. What do you mean? It speeds up everything? What do you mean when you say speeds up?
Forward.
Yeah. Now, the question is why does the forward get sped up?
There's more steps to react.
Yep. There was a theory last chapter that had 3 steps, 3 things. The collision theory. What are you doing when you add more reactants? You have more collisions. Isn't that going to speed up the forward reaction if you have more stuff to collide? What you're going to do when you add a specific either reactant or product, you're going to increase the amount of collisions. Did we increase the amount of collisions of products to go back to the reactants? Did the products get more things to collide with? Like for the reverse reaction? No, right? So the rate of the reverse reaction stayed the same, right? But we added more reactants, so the rate of the forward reaction increased a little bit, and so it had to shift to the right to get back to equilibrium. Okay? Now, let's talk about, this is the why behind everything. I wanted to spend some time going back and reviewing the why of last chapter and applying it to what we've talked about this chapter. We could just now look at Le Chatelier's principle. I can never spell that. Le Chatelier's principle states reaction wants to undo stress. Well, what was our stress? What? Yeah, we added reactant. That was the stress. So if that's the stress, and it wants to undo the stress, what has to happen? It's going to react to remove the reactants, which by default will produce more products. you're probably wondering, couldn't I have just looked at Le Chatelier's principle and completely ignored all of this? You absolutely could have, and you could have answered that question. But it's going to be a little bit more beneficial if you can understand, okay, what's actually happening from a mathematical standpoint? What's happening not only just to the idea of equilibrium, but why? Based on rates. Because equilibrium and kinetics or rates are very much intertwined and very important when you're trying to study these things. You can't really have one without the other. Does that make sense? Okay? So I wanted to at least spend some time doing that so that you can kind of see what is the why behind this. So, can I erase this? Did you get what you needed? Now, this is just a quick summary. You can memorize this, and you can answer a lot of questions with just rote memorization, but I'm hoping that you'll actually have an understanding of the whole picture and not just memorize that. Okay? Addition of reactants or removal of products will shift reactions to the left, and the reason why is if I add reactants to undo that stress, it's going to remove reactants by producing more products. If I remove a product, it wants to replace the products because the stress is removal of product. And the only way to produce more products is to react your reactants. Sense? And then obviously the addition of products or removal of reactants is the same idea, just now going the other direction. Right? So, answer these 3 questions. And we're done. Nice quick, I'll be right back. And it wouldn't be a bad idea to maybe write next to it why you think it did what it did. Like the why behind it. Not just, oh, I memorized or I know that if it does this, it will do this. But why? Alright, what we got? Sorry to take a little longer than I wanted to. Addition of CO, we'll do what? Shift it left. Addition or removal of carbon or your other guy, we'll do what?
Addition with shift, right?
Nope.
No. What?
Because they're solids.
Yep.
Oh, dang.
Didn't do anything.
I was thinking that, but.
It's not gonna do anything. Trick question, I suppose. Did you guys write the equilibrium expression out? Okay. Yep, don't forget that. This isn't gonna do anything. And C will do what?
Shift right.
So we got left, no effect, and right. Now, could I ask you a essay question to explain why it will shift right? Could you say, if you add CO, what that's going to do is increase the amount of collisions your products will have, increasing your rate in the reverse direction? Okay? So what you have is an increased rate in the reverse direction, and so you start shifting and you start seeing more reactants being produced, which will slowly increase the rate in your forward reaction until they get back to equilibrium once again. Okay? That's it.